Okay, good morning. And today we are going to do the last lecture on ensembles in statistical physics, and this will be the grand canonical ensemble. So just to remind you the basic idea, let's look at this picture. On the left, we see what we introduced first, which is a microcanonical ensemble, when the system is isolated and the number of particles, volume of the system, and the energy of the system is all conserved. In the middle picture, we see a description of a canonical ensemble where we relax the condition of the constant energy of the system, so the system is no longer isolated, but number of particles, volume, and temperature is still conserved. Now, I want to relax the condition of a constant number of particles and allow particles to accept. For example, through the membrane, we put some membrane, permeable membrane, volume is still fixed, temperature is fixed, but particles can escape or just can enter the system. This is what basically corresponds to the grand canonical concept. And students from experience, they have considered the grand canonical ensemble to be more difficult to understand and appreciate comparing to the first ones. But it's actually not the case. And from the statistical point of view, this is very natural. So what we are going to do, we are going to build the grand canonical ensemble upon the canonical ensemble by relaxing the restriction to a definite number of particles. So let me remind you that in the canonical ensemble, the main object is the partition function, and which basically describes a distribution, probability distribution for a system, and depending on the energy of the system, we have different probabilities, and the partition function, canonical partition function, basically is the sum of all possible probabilities. Now we are going to relax the condition of the number of particles, and we will introduce the relative probability of finding the system with n particles and temperature T and volume V. T is still fixed, volume is still fixed, but relative probability of finding the system with the number of particles n will be z to n times the canonical partition function for this number of particles. Okay, so what we are doing for different number of particles, we are waiting. For different number of particles, we introduce an additional weight corresponding to this number of particles, this factor Zn. We know that the partition function, canonical partition function, describes the probability distribution with a fixed number of particles. But now we take different canonical ensembles with corresponding to different number of particles, and we multiply them by the probability distribution for this system will be just multiplying the canonical partition function with a fixed number of particles by the addition of factor z to n, where z is a fixed variable, a new variable, and n is the number of particles. And if we now substitute the expression for the partition function as a sum of all probabilities, if you remember that this is sum of all states of the system, and the relative probabilities, they are given by the Boltzmann factor, which is exponential minus beta e. And for convenience, if we introduce a notation for this variable z, which is, by the way, called the fugacity, the relative probabilities or the relative probability of finding different number of particles in the system, then not the relative probability, but the variable which is related to different number of particles. And if we introduce this variable z as being exponential of beta mu, where mu now is some other parameter, then plug it in here, we get this expression exponential beta mu n minus energy of the system times the sum of all energies of the system with a fixed number of particles equal to n. Okay, because this EI, it actually depends energy levels in the system with n particle. So this EI not a constant, it's a function of three variables: number of particles n, volume of the system, temperature, and this is just energy levels in this system. We can visualize this picture now as follows. This is our system. It's allowed to exchange heat with the heat reservoir of temperature T, but now it's allowed also to exchange particles with particle reservoir, so particles can enter and escape from the system. And this is the relative probability of finding n particles at the volume V and temperature T and number of particles. Okay. Now, remember that in the canonical ensemble, once we introduced relative probabilities, we were introduced averages of different values, just weighting different, just measuring different quantities like energy, pressure, etc. We could just we introduced them with different weights corresponding to the Boltzmann factors, and as a result, the internal energy of the system with n particles, the average energy, was given by simply by taking a derivative of the log of the canonical partition function with respect to the inverse term. In the grand canonical ensemble, it's very similar now. We have these relative probabilities ρ of finding the system of the system to have n particles. And so we calculate the average value of any quantity by averaging this relative probabilities ρ over all number of particles. Okay, so this is if we just if this is A is a quantity which we are trying to average with the number of particles n, we multiply it by its relative probability and sum of a number of particles n. And then we divide by the normalization factor just to make it so the average of 1 is 1. Okay. And if we now substitute for the relative probabilities the expression which we just introduced in the previous slide, we get this kind of formula. And here is the summation. Zn is a canonical partition function. And here we sum over all possible number of particles. So as before, as when we introduce the canonical partition function, now it's naturally to introduce this in the denominator. This is a normalizing factor. Okay, so that the average of 1 is 1. So this normalizing factor is now called the grand partition function. And we will denote it as Z crossed. It now depends on this variable, additional variable Z, V and T, or mu V and T, where Z is exponential of beta mu. Mu, as we'll see later, is a chemical potential, but at this stage we don't know it yet. We introduced it into our statistical description simply as an additional variable. And now using this definition, the grand canonical partition function is simply given by the sum over all number of particles of the canonical partition functions with different weights, and weights are equal to z to n, where z is a fugacity. Once we know the distribution of probabilities and how to calculate the average quantity of any observable using this formula. For example, we can calculate the average energy of the system in this grand canonical ensemble. Because remember that the energy enters into the, once we write down the expression over the of the canonical partition function is the sum of all Boltzmann factors, then it's very easy to show. I won't do it, it's a home exercise, but it's quite trivial to show that for internal energy of the system, average energy, we obtain a very similar expression to the canonical ensemble, that the average energy of the system is given by the partial derivative with respect to the inverse temperature of the logarithm of the grand canonical partition function. Okay. Now, so now we have a system with where the number of particles can fluctuate. We have relative probabilities, so we basically have all basic ingredients for our statistical description. As I said before, we can calculate now the average quantity of any observable which depends on the number of particles, and the number of particles can fluctuate, so we can calculate the average value of the observable with a fluctuating number of particles. And obviously, the first observable we want to calculate the average of is the number of particles itself. So by definition, the average number of particles, by the definition of the previous slide, the sum over all possible number of particles in the system. This is our observable number of particles. We multiply it by the relative probability of finding the system of the system to have n particles, which is z to n times the canonical partition function, and then we normalize. And using differentiation trick, you can immediately see that this n, if we differentiate this z n with respect to, if we take differentiate zn with respect to z and multiply back by z, we get this extra factor. So we can immediately see, as we've seen many times in the canonical ensemble, that this can be written as z over dz of the logarithm of the grand canonical partition function. So the average number of particles in the system can now fluctuate, but the average number of particles is given by this kind of derivative. And now let's remember that z is exponential of beta mu. Beta is 1 over kt, so we can express mu as equal kt log of z. This derivative, zd over dz, with this notation for the mu, this is nothing else as a derivative with respect to mu, or with respect to a chemical potential. Indeed, let's check that this is the case. I will try to draw it on slides directly. So let's see. Z d over dz. Z is equal exponential of beta mu d over d of exponential of beta mu. Now beta is a constant, so it becomes equal. When we take the partial derivative, you can use the chain rule here, but it's kind of obvious that this partial derivative is equal exponential of, so you get exponential of beta mu here, and this partial derivative is nothing else as exponential of minus beta mu times d over d mu. So these two exponents, they cancel out, and you see that this is partial derivative is indeed nothing else as the partial derivative with respect to the chemical potential. Okay. So the next question. We know how to calculate the average number of the particles, but as we did in the canonical ensemble, I need to erase that. As we did it for the canonical ensemble, we can now calculate fluctuations. And to calculate fluctuations, we need to calculate the squared average number of particles and then calculate the variance. And this is done exactly as in the canonical partition function, in the canonical ensemble, where we calculate the fluctuations of the energy of the system. So what we need to do, we need to differentiate the logarithm of the grand canonical partition function twice with respect to the chemical potential. Okay? And when we do that, this is the same as applying this derivative z dz twice to this expression. And when you do that, you get two terms. One with n squared, which is n squared average, which comes from the differentiating this factor twice with respect to z. And then when you differentiate it once, you also need to differentiate this factor, and this is the result. You get this contribution, and z over dz, as I explained. Yeah, actually on the previous slide, I missed beta when I differentiate with respect to dz. Do it again, probably. Let's do it again, because on the previous slide, I missed beta. Okay. Go back. Let me do this differentiate again. So, okay, I'm okay. Okay. So z d over dz is equal exponential of beta mu d over d exponential of beta mu. That's equal. This is exponential of beta mu, but when you take the chain rule for this, you need to differentiate this guy with respect to mu, and this will give you the exponential of beta mu. So what we get, exponential of beta mu, and here you get exponential of beta mu, but you also need to differentiate this guy with respect to mu. So there will be an extra beta, 1 over d over d mu. So these guys cancel out as before, but there is the factor 1 over beta here, okay? As 1 over beta is kt. So this is a chain rule. I missed that 1 over beta on the previous slide, okay? So with this notation, we can now, once we know the average squared of the number of particles, we can calculate the variance of the number of particles, which is given simply by the second derivative using this expression, second derivative of the log of the partition function using this partial derivative with respect to the chemical potential. Okay. Now, if we introduce the density of particles, by simply dividing both sides of this equation by the volume squared. Then the left-hand side is the variance of the density of particles, but the right-hand side, because log of z is the extensive quantity, so it's proportional to the volume of the system. So we expect it to be final. But there is another factor here, which comes from k squared t squared over v, because we divided both sides by v squared. And we've seen this phenomenon before. So this factor, when volume of the system goes to infinity, goes to 0. So in the thermodynamic limit, the variance of the density goes to 0 very fast. As a result, the system, the distribution is very sharply peaked near the average number of particles. So in the thermodynamic limit, the great canonical ensemble is equivalent to the canonical ensemble. Okay. So the next question is, now we have a microscopic description of systems with a variable number of particles. We want to connect it with macroscopic quantities like pressure, temperature. Temperature is fixed, like pressure is the quantity of our interest. If we assume that the number fluctuations of particles are very small, and I just showed you in the previous slide that they indeed fluctuations, they're getting smaller and smaller once the system goes large. So we expect that the largest contribution to the grand canonical partition function will be from the average number of particles, okay? Because all distribution is sharply peaked near that average number of particles, okay? So in this case, we can assume that the logarithm of the grand canonical partition function in the thermodynamic limit, which is the log of the sum of the all number of particles, will be greatly dominated by the average number of particles, by the term with the most probable number of particles here, okay? Because fluctuations become very small in the thermodynamic limit, so we expect that almost all contribution to the most significant contribution to the grand canonical partition function will be coming only from a single term, z to the number of particles average times the canonical partition, okay? And taking the log and remembering that z is exponential of beta mu, this term log of this becomes this, and this is the log of the canonical partition function. Now remember that when we studied the canonical partition function, we found that the canonical partition function is exponential of minus beta, the free energy of the system. Fn of Vt is fixed number of particles. Now, we expect that the free energy of this system, it should be an extensive quantity. So we expected that it's proportional to the number of particles. If you double the system, you expect that the free energy of the system will double as well. So we expect that the free energy of the system should be equal number of particles, which scales with this little factor A, which is the free energy per particle. And obviously this free energy per particle, it cannot depend on the volume of the system, but it will depend on the average volume of the system per particle, which is now an intensive quantity. So if we have n particles in the system and volume of the system is equal capital V. Then we introduce the volume of the system per particle, which is nothing else as 1 over the density of the particles, because density of the particles is capital N over V, and this little v, volume per particles, is V over N. Okay, so when number of particles grows, V grows, this is the average volume per particle. So we expect that the free energy of the system should scale like this with respect to the number of particles when N grows. So proportion to the number of particles times the average number of particles times the average the free energy per particle, depending on two quantities, little v and t. Okay, so let's now substitute this canonical partition function in here, log z here, which simply becomes minus beta fn. And for the free energy, we substitute this expression. This is the result. So the logarithm in the thermodynamic limit, we expect the logarithm of the grand canonical partition function. It scales as the average number of particles over kt times mu. This is this term. And the second term, this will be minus beta fn. And for fn, we substitute this expression. And this is the second term, the average free energy per particle, depending on the average volume per particle in the system. Now, let's remember that in the thermodynamics, so at this stage, this is a completely microscopic description. We didn't make any connections to the canonical to the thermodynamics yet. So we started with the grand canonical partition function. We showed the fluctuations are small, so this should be the dominant contribution, but we still don't have any connection with, and this is all statistical description. Now, in thermodynamics, we know that if you have the free energy of the system, if you differentiate it with respect to the volume, this is a misprint here. This should be, let me correct it. This should be, annotate. That should be the number of particles here, and fixed. So the pressure is equal minus, in thermodynamics, we know that pressure is minus the partial derivative of the free energy with respect to the number of particles at fixed n and t. And if we substitute for the free energy the expression as n times the average number of particles of the volume per particle over t, it becomes minus n d over dv. Okay, but this quantity, remember that this average volume is the capital volume V over capital N. So let me write it again. Little v is equal large V over N. So when we differentiate, if we substitute this little v in here, and if we differentiate with respect to V, then we will get with respect to the capital V, this expression, what we get is get the extra factor 1 over n, which cancels out this factor, and this the expression of the for the pressure in terms of the free energy per particle. Similarly, we can calculate the chemical potential of the system, differentiating the free energy of the system with respect to the number of particles at fixed volume and temperature. When we do that, we again substitute here the expression that Fn is equal n times little a depending on little v and temperature, and differentiate with respect to n. A dependence on n here intends two terms, here n and in little v via this formula. So when we differentiate with respect to this n, then we get this term. But we also need to differentiate with respect to n in here, n d over dn, okay? A of vt. And if we do that, we again substituted v here as v capital over n. Let's do this exercise. So we need to differentiate d over dn, little a, which depends on capital V over n. And I will drop a dependence on t, because t is a constant. And this is nothing else as when we differentiate with respect to n, what we get, we need to differentiate this factor with respect to n, which what we get, it will be minus v over n squared, okay, times a prime with respect to little v, okay? So once I plug it in here, I see that there is an n here, and here it cancels, and so I get minus v over capital N, which is my little v, a prime. And as a result, I get this expression. Chemical potential is equal the free energy per particle minus the v times the partial derivative of the free energy per particle with respect to v. Okay, so let me erase this. And so I have this formula. And using the result for pressure now from the first equation, I can substitute the expression for the derivative of d over dv equal minus pressure and use it here. So d over dv becomes minus pressure, and I get from the thermodynamics that the chemical potential should be equal times A times Vt plus P volume per particle. And now let's compare it with our formula, which comes with the statistical description. So we have log of z is number of particles over kT minus times mu minus the free energy per particle. Now, if we take this expression coming from thermodynamics, substitute it in here, okay? So we see that as a result, let me do this calculation again. In the right-hand side, then we substitute, we get n over kt, and the expression in brackets becomes a minus av, it becomes p little v. But this is nothing else as n over kt times pressure times little v is number volume per particle. So it cancels, and we get pressure in the system, volume in the system over k. Okay, so it means that the right hand side of this expression is equal PV over KT. So if we introduce a microscopic quantity, the so-called grand free energy, or sometimes it's called grand free potential, capital phi equal minus PV, then this capital phi is equal minus KT log of Z, where Z is the grand canonical partition function. This capital phi is obviously a macroscopic quantity, Oh, no. Okay. PV is a macroscopic quantity, but this phi we define as in terms of the grand canonical partition function, which is the microscopic quantity. So this is a microscopic quantity. This is a macroscopic quantity. So we found a relation for the grand canonical ensemble between microscopic and macroscopic descriptions. And in particular, if you remember, we can introduce the grand free potential in the thermodynamics, and it's given by in terms of the internal energy, entropy, and the number of the particles. It's differential. This is just to remind you what the grand potential in thermodynamics, how it's defined. But now we have for this grand potential its description in terms of the grand canonical partition function. Okay. Okay, let's go back and let's go ahead. Okay, so let's look again at this formula, which says that log of z is equal, when I substitute PV over KT. This expression, we calculated this. The right hand side was PV over KT. And this is the macroscopic relation we derive, that the pressure over KT is equal to 1 over LV log of Z. Okay? So we found the pressure as a function of temperature, volume, and this little variable Z, which is fugacity of the system. So now let me remind you that we calculated before the average number of particles in the system, which was the average number of the particles in the system, which was d over d mu of log of z, okay? Which is the same as z d over dz of log of z. Now, this capital N is nothing else as the density times V. So we can write the expression for the density, which is the second equation, as 1 over V, Z over dz, log of Z. And these two equations now provide us with the equation of state. What does it mean? Assume that we have a system with a given fugacity. Then we can calculate from this equation the average number of particles, or the density of the system. But assume that now we have the density is given. So, or we know the average number of particles in the system. Then we can look at this equation as an equation. Of course, this is hard to solve, but this, once n is given, this becomes the equation for the fugacity for z. And if we can find for a given n the fugacity, then we can substitute it in the first equation and get the pressure. And this will give us the equation of state in the system. So of course, these equations, two equations, are not possible to solve exactly. But what we can do use series expansion. And this series expansion, it's called virial expansion. In the gas phase, it's usually possible to expand the right-hand side of these both equations as power series in fugacity. Okay? So this, how these expansions look like. So let's look again at these two equations. Pressure over KT is equal to 1 over V log of Z. This is, we know that log of Z, which is a grand canonical potential, it will scale proportional to the grand canonical potential. It will scale like proportional to the volume of the system. So this is an intensive quantity in the right hand side, and we can see that it's indeed an intensive quantity. So P over KT, if we expand it in series of fugacity, and this is a typical expression, then we expect a Taylor series in powers of z, starting from the term z plus z squared with some coefficients. And then this should be an intensive quantity, but there was a volume there. So this we should have some, we need to put some quantity which is proportional or has the dimension of the volume. And this is normally, it's convenient to put 1 over lambda cube, where lambda is the thermal length in the system. And similarly, for the second, if we have this expression, if you look back here, we need to take z log of z this and differentiate it z over dz. So we need to take the right hand side of this expression and differentiate it with respect to z and multiply by z. When we differentiate this with respect to z, it will give us L times z L minus 1, and multiplying it by z, we get this. Okay. So these two expressions, they give us the equation of state. How come? For example, the number of particles is fixed. For the classical system, fugacity is small. So in principle, we can solve this equation and find z as a series in the concentration of the as a series in the density of particles in the system. So somehow inverse this relation for writing z as a series in the density. And then we substitute it in here, expand series, and we can derive the pressure over nkt times density, PV over nkt, as a series in density. Okay, for a small density. So this is the virial expansion. For the, say, left-hand side, we can look at the first approximation. This is basically the corrections to the ideal gas law. For low density, when n goes to 0, we see that the leading contribution is given by PV over nkt and simply is 1. When n goes to 0, this is the ideal gas law, and when n grows, we get the corrections in density of the system, and this series is infinite, and coefficients at each term here, A2, A3, they are called cluster integrals and express correlations among a cluster of L particles due to interactions. So once we express z from this expression and substitute it into this expression, we get the expression for the PV over KT. And these coefficients can be measured numerically, and there are also some technical tools to calculate it, and they give you basically corrections to the ideal gas law when concentration of particles grows. When the density of particles becomes high enough, then the system approaches the quantum regime, then this series will simply diverge. And in this case, you need to switch to the quantum description. Okay, I will stop here the first part and then continue in the second part.